Hello again, this is Toby. Today we'll be talking about working with time and Solidity. So what we'll cover Solidity units and global variables, creating a basic saving contract, creating a basic staking contract, okay? So what are Solidity units and global variables? Global variables are special variables which exist in global workspace and provide information about the blockchain and transaction properties. So basically these global variables allow us to access specific attributes and properties of the blockchain at a specific moment. Okay, so we have examples: block hash, the hash of the given block; block Coinbase, the address of the miner that mined the current block; block difficulty, okay, block number; block timestamp; gas left. Gas left returns the amount of gas left during the transaction. Message of data, which returns the call data, okay, the complete call data, useful for when you're writing assembly. We have message of sender, which is the address that triggered the operation. We have message of sig, which is the identity or signature of the function that was called. We have message of value, which is the amount of ether in way that was sent to the contract function. Then we have transaction the gas price, which is the current gas price, and transaction the origin, which is the initial address that created that called contract, but basically started the transaction. Okay. So we have units. Units are suffixes we add to literal values of variables, basically to change their behavior or modify their content, basically. So most likely we use them to denote placeholder values or place values to, okay, so to denote like larger values and to abstract the need for multipliers. That's why we use global units. Okay, so we have one way, which is equal to 1. So there's a way unit to in Solidity that we can use to refer to a way. Okay, we also have a GUI, which can abstract the logic of multiplying out a single value to produce a GUI. So one GUI is equal to 1 raised to the power of 9. Okay, so that's the abstraction. So if you add GUI to the end of a number, you're basically multiplying it by the power of 9. Okay, same thing for ether. If you add ether to the end of a number, you're multiplying that by 10 raised to the power of 19 too. So it's same thing for time units. We have a second, minute it's 60 seconds. So 1 second is the same thing as a single number unsigned integer 1. 1 minute will be the same thing as 60 times unsigned integer 1. Same for hours, same for days, same for weeks. Okay, so we're going to get right into the code. Okay, so if you've not yet set up your development environment, I advise you refer to the official Truffle guide and documentation. Basically they will show you how to set up node, npm, and install Truffle globally. Okay, so next things would be to create a project folder. So you can go ahead and follow the steps, and we'll create a new Truffle project, Truffle init, to create a new Truffle project. Okay, since we're going to work with external libraries, we're also going to have to create a node package or node folder. Okay, so once you've gone ahead to set up your project, the next steps would be to start writing contracts, basically. So you use create all. Truffle create all will create a contract folder, contract Solidity file rather, a test file, and a migration file for each argument. So in this case, we're going to create a Solidity file for time savings, a test file, and a migration. Same for basic staking. So I believe we can get straight into the code. Okay, let's first of all explain what we're going to be doing, starting from the basic saving contract. So we're going to create a simple contract that allows you to deposit an amount of ether and set a date to withdraw. Okay, so after the set date has been reached, the money can be withdrawn by calling a public function. Before this time, the money or ether will be unavailable. So this is like a very strict piggy bank. Okay, so you can deposit an amount, set a date when you want to withdraw it, and then only after that date will you be able to withdraw that amount. So let's look at the structure. We're going to have a fallback function. Okay, this is just to display how fallbacks work in Solidity. So fallback functions are called whenever an address transfers ether to a contract without calling a specific function. Okay, so just like a catch all or catch all exceptions are basically. So anytime somebody transfers ether to our contract without calling a specific function, the fallback function gets called. Okay, then we have deposit amount. Okay, so this is also another function that accepts ether. and it can only be called by the contract owner, because like it's only the contract owner that can deposit and receive from this contract. Okay, and you also have withdraw amount that allows owner to withdraw a part of his deposit after the set saving time. Okay, so you can call withdraw amount to basically access your piggy bank and like pull out funds from it. Okay, then you can have close account. Okay, so this closes down or deletes your contract and sends all Ether balance to the owner. So basically this is when you like break your piggy bank. Okay, so you've basically destroyed your contract and you've withdrawn all Ether saved in the contract to your address. Once again, this can only be called by the owner after a set saving time. Then balance gets the amount of Ether currently saved in the contract, so it just gets the balance of the contract at that specific point in time. Okay, so it's worth pointing out at this point that blockchain and Ethereum in specific use Epoch time format to store time. Okay, so Epoch time format is the number of seconds since the epoch in, I believe, 1970. So it's not exactly human friendly, so you can make use of this tool to convert from human readable formats to epoch and vice versa. Okay, so let's get straight into the code. Okay, so time savings. Okay, so we have our usual pragma specifying the version of the compiler we're using. Okay, so just wanted to explain something about the fallback and something else called the receive function in Solidity. So if somebody sends Ether to our account, okay, to our contract rather, and they don't call a specific function, there's a specific way that Solidity is going to resolve which function to call. So first of all, somebody sends Ether. Okay, first thing Solidity is going to check is message or data empty, basically. So that's going to check, did they pass any parameters, did they call us, did they send us any call data, basically. If they didn't, we're going to just walk through with the fallback function. Okay, if they did, we're going to, and receive exists, okay, we're going to call receive. If they didn't, we're going to call fallback. Okay, so that's how Solidity resolves which function to call when Ether is sent to a contract but no function is called. Okay, so our actual contract for today is going to be called time savings. Okay, so we have a little nat spec comments, okay, that detail what the contract is about. So we have a title, we have an author, and we have a short description in the notice section. Okay, so first thing we're going to have is an event, or two events rather. So there's going to be a deposit event that's going to be emitted whenever somebody deposits, which is most likely going to be the owner. Okay, so we're going to have index timestamp and an amount. Index allows the front end to search on that field, basically, so they can search for like based on timestamps before or after, greater than or less than. Basically, that's what index allows us to do. Then we have another state variable, owner. Okay, so this is going to track the owner of the account, basically the address that is using the account to store and to retrieve his funds. So there's a bit of nat spec to there. There's a short description and it just basically details how that state variable works. Okay, so if you notice, we also added public, which inherently or implicitly creates a function called owner that we can call to see who the owner of this contract is. Okay, same for withdrawal date. Withdrawal date is the earliest date an owner can retrieve their funds from the smart contract. Okay, so it's another state variable, public too. So we have a function that you can look up to see the withdrawal date. Okay, so we're not going to set this explicitly. Okay, we're going to do a slight calculation to calculate when our withdrawal date would be. So we don't want end users to have to fiddle with epoch timestamps and stuff like that, but we'll look at that in the constructor. Okay, so we have a couple of modifiers here. Only owner, which is going to ensure that it's only the owner that can call specific functions. Has sufficient balance, checks that the amount that we are trying to call from the our contract is less than, okay, or is within the bounds of the contract balance. Basically, this would come up when we have like withdraw. Okay, so withdraw a specific amount, we have to check that that amount is already within the contract balance. Okay, and we have another one called after date, which is a modifier that checks that the current time or the current date is after, okay, a specific date. So that's just our three modifiers. Then we can take a look at our constructor. Our constructor is rather simple. Okay, so we have a single parameter, number of days. Our constructor is also payable. Okay, so payable allows us to pass some ether while we are sending or deploying our contract basically, so we can both fund our contract while deploying at the same time. Okay, so withdrawal date is equal to block.timestamp times number of days times 1 day. Okay, so this 1 day abstracts the logic of like converting from seconds to hours to minutes to days. Okay, so we just have them send in a single day or number of days they'd like to leave their money in the contract, and we multiply that out and save everything in a withdrawal date. So this is going to store the epoch timestamp. Okay, so once again we see the need for units, so that abstracts all the logic of converting from minutes, seconds, days. Okay, then we also set owner to equal to message or sender, so the address that deployed this contract is going to be the owner of this contract. Okay, so we see our fallback function again. Okay, so simply it's going to check that the owner is the sender of the function basically. So fallback is called when somebody sends ether to our contract, so we're going to check that the right account is sending ether. If they don't, then we're going to revert the transaction. Then we're also going to emit a deposit, okay, of the date that the deposit was made and the value, okay, that was deposit. Same thing for deposit amount. Okay, so only owner modifier does the same check, requires that the sender is the owner. Okay, it's also payable, so that means it accepts ether. Then we're going to return a bool that the transaction was successful after emitting an event deposit. So a rather simple function. Okay, then we have withdraw amount, which just takes in an amount. Okay, checks that we have a sufficient balance, checks that the date we have passed our withdrawal date. Okay, then it sends that ether to this address. Okay, so first of all cast it to a payable address, then we now send it this value. Okay, then we forward it all gas that we have left. Okay, then we check that it was successful with sent. So call is going to return a bool and data basically. So boolean being that sent, okay, that the transaction was successful, and if that is true, then we move on. If not, we raise an error, fail to send ether. Okay, then we have close account, which is basically what the contract owner is going to call when they want to break their piggy bank basically. So they're going to call this is going to destroy the smart contract, delete all its bytecode on the blockchain, okay, and revert all ether or transfer all ether to the owner's address. Okay, so once again only owner can call this, and it should be only after the specific date, which is the withdrawal date. Okay, then we have balance basically. So balance is going to return a balance, or basically the balance of the contract. So balance is going to equal to address this dot balance, so we cast this to an address and then we get its balance and return it. Useful for knowing like how much ether we have left in our contract. Okay, so that's just the basic code. Obviously we don't have a lot of NAT spec comments here because I'm trying to make this as concise as possible, but if you were to write for professionally, you'd have to write comments basically to explain what your code is doing. Okay, so that's the basic saving contract. Next, okay, and to our next contract, which is basic staking contract. Okay, so we're going to extend an ERC20 token, okay, to support staking and rewards. So we're going to handle rewards and staking within the ERC20 contract. Okay, we're not going to have a manager contract. User can stake some of their tokens. Okay, when they stake their tokens, they effectively are locked and can be transferred or spent. We're also going to have a reward system where users can earn 1% of their stake. They will be able to claim rewards weekly, and users who do not claim their rewards effectively lose them for that week. Okay, so the idea is that we're not going to reward users for leaving their rewards for a longer period of time. So the quicker you claim your reward, the better for you. Okay, so you have to monitor the contract and monitor your deadline to know when you can claim your reward. Okay, so we'll be using a rate of 1 ether to 1,000 tokens. Okay, so if we have a single ether, which is equivalent to 1 raised to the power of 18 way, we'd have 1,000 tokens would equal to 1 raised to the power of 18 way. Okay, so 1 way would equal to 1,000 divided by 1 raised to the power of 18, or 1 exponential 18, which equals to 1 divided by 1 exponential 15, or 1 raised to the power 1 exponential minus 15. Okay, but since Solidity does not allow us to express floating point values, we will leave it in this sense. Okay, so most of the time when you are writing your logic for buying or trading tokens, okay, you would have to write this specific to your exchange rate, and in a way that's easy for you to track and implement. Okay, so it's more usual for you to have like multiplications, but in a case where you have greater value of for your token per ether, okay, you might sometimes need to divide. Okay, but there are multiple ways to express this logic and express this ratio. Okay, I just picked this because this would be simpler. Okay, so when you just call by token, we are going to divide their message.value by 1 exponential 15. Okay, note that we did not account for decimal places of our token. Okay, so our contract structure, in addition to the standard ERC20 interface, we have the following functions. So on top of the ERC20 interface of transferring, transfer from, approve, and allowance, we are going to have the following functions. Buy token. Buy token allows users to buy tokens by sending ether to the function. Okay. Stake token allows users to stake their tokens to receive rewards. Takes a parameter of the amount to stake. So you're going to stake from your balance. You cannot stake tokens that you do not have, basically. So once you've staked your tokens, you cannot transfer them or you cannot spend them. Okay. We're also going to have claim reward. Claim reward allows users to claim rewards for their stakes. Implement checks to ensure the minimum stake period has been met. Okay, so you're supposed to call this weekly from the question. Okay. Modify token buy price allows admin or owner of the smart contract to change the exchange price of the buy rate, basically. So they would be able to change the logic behind buying tokens. Okay, so it would increase in value or decrease in value. The admin has the opportunity to change that value. Then we're going to have a big red button, basically, which allows the owner to destroy the contract. So we're going to illustrate how self-destruct works. Okay, so useful in cases of emergencies or hacks, or when we want to just call a stop to the whole process, we can destroy our smart contract and all the logic. Okay, so let's get straight into the code. Okay, so basic staking contracts. Okay, so apart from it, we have our pragma. Okay, we're also importing OpenZeppelin's ERC20 live contract or contract implementation. So it'd be best if you had that pre-installed. Okay, you can see I have OpenZeppelin's library installed. Okay, so we have comments detailing like details of the contract, title, author, notice. Okay, so first thing to notice is we are inheriting ERC20 OpenZeppelin's implementation. You can take a slight look at that there. Just okay, so lots of code here. Important thing to know is that they have defined all the interfaces or required functions for us, so we do not need to do that. Okay, so first thing we have is an event staked. Okay, an event claimed too. So it's an event on top of the already predefined events transfer and deposit. Okay, we're going to have staked and claimed. Stake to be called or emitted whenever a user stakes some of their tokens. Claimed, same when user claimed their tokens. Okay, just for login purposes. So because of the contract we're inheriting, they've already defined the following variables for us. So there's a mapping of balances. Okay, but this is private. Okay, so what private means is that balances can only be accessed from within the ERC20 contract. So even though we are inheriting from it, we cannot access that variable. Okay, you must have another one called mapping. Okay, allowances, basically, which tracks the allowances. Okay, still private, so we cannot access that directly or modify that directly. Total supply, name and symbol are same. Okay, so on top of that, we're also going to have our own values. Okay, so there's going to be staked. Staked is going to be a mapping that tracks the amount of tokens that has been staked by each address. And then reward due date, which is going to track the timestamp that is valid for an address to withdraw, basically. So each address is going to have a specific withdrawal date for each address. Okay, so in light of this, you're going to see that each address can only have a single stake. Okay, so if you add more to your stake, you would modify your old stakes claim date, basically. So one way to work around that would be to maybe implement a mapping that had like hashes of each stake to each user. To be more condensed or complicated data structure. Okay, but as it is now, each address can have a single stake. Okay, so we have another address public owner. So we also have implicitly a function called owner that we can call to check the owner of this address. Okay, then we have minimum stake period, default value 0 days. Okay, so this is the period before you can call claim reward to claim your reward. Then we have token to weigh rate. Okay, so to explain this more. Okay, so this is basically the exchange rate from one token to one way. Okay, so since a token has more value than a way, when we get a way, we're going to divide that by our preset value. Okay, so in this case, 1,000 tokens to 1 ether would be dividing each way by about 10 raised to the power of 5. In this case, we are considering our decimal places, so this token has 5 as decimal places, so we basically multiplied out our previous value by 10 raised to the power of 5. Okay, then we have reward percentage. Basically, this is the percentage that each address is rewarded weekly for staking their tokens. Okay, so it could be easily modified to maybe 10%, 50%, 200%. Okay, that's up to the admin. Okay, so we have a couple of modifiers: only owner, sufficient balance, reward is due. Okay, so apart from the other two, which are other explicit in nature, reward is due is going to check that user can claim reward, basically that their reward is valid, basically. So if it's not so, we're going to throw an error: required date for claiming a reward has not been reached. Okay, so we're going to return back control back to the calling function. So those are our modifiers. So our standard functions, we're going to have a constructor and a fallback. Okay, so our constructor is going to take in 2 parameters. Okay, first one is stake time. Stake time is the same thing as minimum stake period. Okay, then we are going to take in token to way rate, which is the exchange rate of token to way. Okay, so this is configurable when we are deploying. Okay, but for the sake of this task or contract, we're going to use this value based on our question, which is 1,000 tokens to 1 ether. Okay, so safe mint owner initial supply of 1,000. Okay, so basically we're going to just create an initial value of 1,000 tokens. Okay, so we're going to give the owner 1,000 tokens. Okay, we're going to mint them 1,000 tokens initially on construction or deployment. So what safe mint is going to do is going to update total supply to reflect these newly created tokens, and then it's going to update balances. Okay, we'll get to that shortly. Fallback function, okay, it's going to be called whenever somebody sends ether to our contract, okay, but doesn't call a specific function. Okay, so in that case, we are going to calculate the tokens that they ought to have bought with the value they sent to us, and we're going to mint that for them on their behalf. Okay, then we are going to having public functions. Okay, so these are the functions that end users are going to interact with. First of which is buy token. Buy token is payable. Okay, so it's going to return a bool status of the transaction and the number of tokens bought. Okay, so tokens bought is going to be calculated by an internal function. Okay, based on the value of number of way that was sent to us, and we're going to mint this newly bought tokens to the address sender, and we're going to return true, and we're also going to tell them the amount of tokens that they bought. Okay. Stake token also going to be called by end users. We're going to take in a parameter of the amount to stake out of their balance. We're going to check whether this specified value is valid for that account, whether that account has such enough balance to make such a stake. Okay, I'm going to return a boolean of the status, and then timestamp basically of the reward time. So like I said earlier, the blockchain works with epoch timestamps and epoch time frames. Okay, so time is stored in epoch format, which is the number of seconds since the epoch in 1970. So reward due date, we're going to update that with the block timestamp plus minimum stake period global variable. Okay, so we're going to update the reward due date for that address. We're also going to update the user stake. Okay, so initially each user stake is going to be 0. Each time they call stake token, they're going to update that stake. Okay, so we're going to return these values basically to the end user. Okay, so claim reward. Claim reward is what the end user would call to claim their rewards and update their balance. Okay, so first of all, we're going to check or ensure that their reward is due. So this sender or this address has the ability or the right to call for their rewards. Okay, so this is going to be determined by the minimum stake period. If the stake has stayed for long enough, then they have the right to call claim period. Okay, so we're going to return a boolean that tells us the status of this transaction. So first things, we're going to reward it is going to handle the logic of confirming that this address is valid. Okay, for calling claim reward. So we can go straight to the logic. First thing we're going to do is update reward due date. Reward due date, we're going to add basically refactor the next time that this address has the right to call this function, which will be the current time block.timestamp plus the minimum stake period. Okay. Then we're going to also calculate the reward for this user or for this address based on their stake and the reward percentage for their stake. We're going to mint this new reward to the user. So interesting to know that we are not unstaking their tokens for them. We are only giving them new balance or more balance, basically minting new tokens to their balance. Okay. Say next function we have is modify token buy price, which will be called only by the owner. It's going to take in a parameter of the token to wear rate, the new one. Okay. So the admin could change the token to wear rate if they so please. Okay, so now we get into internal utility functions basically that we use throughout our contract basically to abstract logic and make things more manageable. Okay, so first thing is safement. Safement is a function we use to abstract minting. Okay, so it wraps around ERC, opens up the implementation of mint. Okay, so we're going to have an address receiver and the amount to mint to that address. Okay, so we're just basically going to call ERC20's implementation of mint. Okay, then return true. Then we have calculate tokens bought, which calculates the amount of tokens bought based on the value passed into it. Okay, so first things first, we're going to check that they have passed the minimum value to buy a single token. Okay, if they have not, we're going to revert the whole transaction because they wouldn't get any token for their money basically, so it would be wasted. So we revert the money back to them. Okay, then we calculate our token amount. Okay, once again I repeat, there are lots of ways to calculate this amount based on your implementation and your values, okay, and your variables and target like exchange rate. Okay, but I chose this because this is rather simple. Okay, so we return the token amount. Okay, then we have calculate reward. Calculate reward is going to calculate the reward for each taker based on the amount that is staked and the reward percentage. So that's straightforward. Okay, so important to note, it's usually advisable to multiply before dividing in Solidity to avoid like unpredicted truncations, okay, and unpredicted overflows and underflows. Okay, so Solidity from version 8 upwards has support for overflow and underflow protection, so there's no need for OpenZeppelin's safe math library anymore. If a transaction or expression is going to overflow, Solidity by itself is inherently going to throw an error. Okay, so we're also going to look at the OpenZeppelin overrides. Okay, because we inherited OpenZeppelin's implementation of ERC20, we have some changes to be made to give us the behavior that we want in our contract. So first of all is that I changed the number of decimal places from 18 to 5. It's usually advisable to leave it as 18 for interoperability. Okay, so to make things easier and more manageable for like other platforms, but for this particular contract I chose it to be 5. Okay, we don't need that such a high level of precision. Okay, next thing we're going to have transfer function basically. So because we have the idea of locked tokens, okay, and we do not want users to be able to move around their locked tokens, okay, we have to override OpenZeppelin's transfer function and make it consider our locked tokens. Okay, so it should consider that the amount that the user wants to move around should be less than his balance, and should be less than the amount of locked tokens too that he has locked. Okay, so he can't move around those locked tokens. That's the whole idea. So we override it. Okay, and so we just make sure that it has sufficient balance, okay, from an amount basically. So we just attach our previous modifier to it, and then we call OpenZeppelin's implementation of ERC20. So that's the beauty of modifiers. Okay, and then the final function is big red button basically, which allows us to shut down our contractor smart contract basically if we run into any emergencies or the owner feels such as to shut down his function. Okay, so self-destruct is going to clear all the bytecode of this smart contract. Okay, so it's relatively useless, and it's going to transfer all the balance of the smart contract to the owner's address. So that's how these smart contracts work. Okay, so this is a basic staking and reward system implemented purely with Solidity. Okay, so we extended an ERC20 contract to include the functions and related variables basically to allow us to perform staking and rewards. Okay, so we can take a look at just the deployment scripts for time savings. Time savings has only a single constructor parameter, so we can deploy it with a number of days before withdrawal. Okay, same for basic staking. So we can have a minimum stake period of like 7 days, Okay, and we can have a token to weigh rate of 10^10, I believe. So that's how you would implement a basic staking and reward system per address. Okay, so once again, the behavior you want in your Solidity contract is usually limited to a specific use case. Okay, so generic applications or implementations may not always work. Okay, so it's mindful to be to consider that when you are working with smart contracts. Okay, so thanks for listening. Okay, and today we have looked at working with time in Solidity. If you'd like to deploy your smart contract, you can follow the deployment process outlined previously. Okay, you can also go to the resource I showed earlier on how to generate a mnemonic for deployment. Okay, if you run into any of the following errors, these are things you can try to sort them out. Okay, you can use legacy OpenSSL on the latest version of Node, which is like 7 point some. And for slow connections, you can increase the number of network connectors basically in Linux environments. Okay, so thanks for listening and looking